In this screencast, I want to show how you can actually start with a vector space and then create a subspace from that vector space. A subspace is just a subset of a vector space that is, again, in its own self, a vector space. So the example we're going to start with is, we'll let V be the set of functions defined on all the reals. We've already shown in the second screencast that this function, this set V, is already a vector space where we're using addition of functions and scalar multiplication of functions as usual. So polynomials, I'm going to define P of x. This is the set of polynomials. What is a polynomial? Well, 1's a polynomial. 3 plus 4x is a polynomial. 7 plus x squared minus x to the 40th is a polynomial. The only key is the integers, the x to some integer power creates a polynomial. So you could look at this as an a plus bx plus cx squared plus dx cubed plus dot dot dot, but you got to stop somewhere. And so you have to stop at some power, x to the n, and then we need some variable in here. So polynomials, well, are they a vector space in and of themselves? One option is to check all of these axioms. And that could take a little while. We'd have to go back and do everything we already did before. However, we're going to discover a bunch of things. We already know vector addition is associative because it is on the set of functions. We already know vector addition is commutative. We don't know there's a zero vector in the set of polynomials, but we can show there is. So, the key thing we have to look at is there a zero vector? We need to look at A3. Is there a zero vector? Additive inverses are going to come automatically from here. We're also going to get scalar multiplication distributing, being associative, and multiplication by 1 does nothing. All of that comes from the fact that we are a subset of the set of functions. So the only thing that didn't come was A3, but we also have another thing to check. 1, is addition closed? Is the sum of two polynomials a polynomial? And is a scalar multiple of a polynomial a polynomial? So really what we need is we have to check these three things. If we check these three things are true, then the rest of the vector space axioms all come from the fact that we're a subset of the functions defined on all reals. So all we have to do is show is 0 in the set. Well, the polynomial P of x equals 0 is a polynomial. And closure. If I take a polynomial and I add a polynomial, this is a polynomial. So it's closed under addition. And if you take a scalar and you multiply by a polynomial, this is again a polynomial. Hence, this set, the set of polynomials, 0 is in it, it's closed under addition, it's closed under multiplication, and since it satisfies all three of these, P of x is a vector space. Now, was that a whole lot faster than showing all 10 of these? By golly, yes. We only have to check 3 things. I'll look at another one. Suppose we look at the set of polynomials of degree 2 or less. Is this set a vector space? Well, first of all, the set of polynomials of degree 2 or less is a subset of the set of polynomials. And do I already know this is a vector space? Yes, I do. So this is a set. I just need to ask, is 0 in the set? Well, the set of polynomials of degree 2 or less. 1, the function 0. That's, we'll say it has degree 0. So it's in this set. 2, if I take a polynomial, so a plus bx plus cx squared, and I add it to another, d plus ex plus fx squared. Well, this is a polynomial of degree 2 or less. The reason I say or less is because if c, this is 1, and f is minus 1, could it be that the sum ends up making the x squared terms vanish, which means the degree drops? And that could happen. That's why I need to include this or less. Currently, the sum of two polynomials of degree 2 or less is again a polynomial of degree 2 or less. And then 3, if you take a constant and multiply it by one of these polynomials, so I'll make the constant k and I multiply a plus bx plus cx squared, it is again a polynomial of degree 2 or less. The only thing that happens is I just times each of the coefficients by k, which doesn't change the degree of the polynomial. So again, here we have this set of polynomials is a vector space. It's a vector subspace of the set of all polynomials. We're going to be showing that things are vector spaces from now on by referring to the fact that they're subspaces of some bigger space. One last one I want to look at, and we'll look at that in another screencast. That completes this one.